Okay, so the way I do these problems is I like to do diagrams to kind of see what's going on. It says a rescue boat just picked up some sailors in a lifeboat. Now the rescue boat is heading north. All right, so they're going north at 29 kilometers per hour. Kilometers per hour. The lifeboat, which they abandoned, okay, so that would be still here, is drifting south at a speed of 4 kilometers per hour. 4 kilometers per hour. And so this is where they were together, and this is rescue boat, lifeboat. Okay. How long will it be before the rescued sailors are 71 kilometers from their lifeboat? So we want this distance right here, this total distance, to be 71. You with me? Okay. Well, first of all, I'm going to draw it like this. Yeah. Most of them, like most related, or these like distance equals rate times time problems, it's side by side. Like it's like someone riding a bike or something like that. Or at least I'm kind of used to seeing it that way. Okay. Okay. Well, there's one thing that we know that's the same. Like, like distance, if you go distance equals rate times time, one of these numbers is going to be the same. Like, is it the distance both of these things traveled? Will that be the same? Like, is the lifeboat going to travel the same as the rescue boat? No. Are their rates exactly the same? Mm-hmm. They're kilometers per hour, so the kilometers per hour of the rescue boat is the same as the kilometers per hour of the lifeboat. Oh, but the time traveled, is that the same? Mm-hmm. So they're drifting apart. Like, well, one's like speeding along, and then the other one's like drifting. And then at a certain time, I'll just say like, I don't know, 1 hour. That would be impossible. No, 71. Let's say like this is 30, so like a little over 2 hours, I guess. Like 2 point something hours. You're gonna stop the time, freeze frame, and they're gonna be exactly 71 kilometers apart. Um, so what of these numbers is there one number that is the same for both? Okay, so like basically it's like a. Can you picture the scene? Can you picture like, all right, like they're both right, and now picture it like iMovie or like your phone like video player, how you can kind of fast forward and rewind, and if you fast forward, it'd be like da-da-da-da-da-da. They'd be like over here, and if you rewind it, it'd be like da-da-da-da-da-da. They'd be closer together. So when you fast forward, and it's like you make that fast forward sound, da-da-da-da-da, and then this far apart, you stop it, and on the bottom, it's gonna say something like, no, time, right? You're stopping it at a certain time. So they've both like let's just say like on this boat, um, on this boat, you're rescued and you put on your stopwatch. And then this guy over here, we forgot about him. He was left on a lifeboat because he was sleeping, and for some reason in his sleep he turned on his stopwatch. Well, at the they're gonna drift apart, and then we're gonna stop the time, and it's gonna say for this person, and it's also gonna say for this person, and at that moment they'll be 71 kilometers apart. Does that make sense? Yes. When the time is the same, they'll be the same distance apart. The time is always the same. The time will never be the time will never be different for this type of problem. Why? Um, Hold on. Okay, so like this is like one boat, and this is like the other boat, and they're drifting apart. Um, so this one goes like that, and this one goes like that. But if I'm like like a third person just watching this whole thing happen from like a mountain with my binoculars, I'm over here, and this is my stopwatch, whatever. No, it's digital, and like right as they're like going like this, they're like going like this. How many stopwatches we have going on here? One. And then I say stop. And then I'm like, guys, drop your anchors. Drop your anchors. Let's measure your distance. That distance that we're looking for is 71. So we're trying to find what time will it take for them to be 71 kilometers apart. Does that make sense? You fully get that? Okay. Because when you do these types of problems, um, sometimes you want to look for the um, which one of these variables is the same in both situations. For example, sometimes you'll have Vivian on a bicycle going from her house to school. And so that's her house and that's the school. But Vivian has a flat tire or some kid punched a hole in her bike tire, and so she's got to walk home, right? So she walks her bike home. Well, is the time going to be the same on this trip as it is on this trip? But the distance is. So in this problem, we know that D is going to be the same. But for this problem over here with the boats, we know that T is going to be the same. So sometimes my first approach would be like to think about like, okay, which one of these in this problem is unchanged? And in the Vivian bike example, the distance is unchanged. But in the lifeboat example, the time is unchanged. All right, so I picked the name Vivian and bike example for a reason because I think that exact problem is in your flashcards. Okay. Yeah, I think her name is Vivian. And I think she got a flat tire. There's a bunch of them in flashcards. I can Did you didn't find any distance problems? There's a chunk of them together. I can show you if you want. Um, okay, so I like to do the distance equals rate times time box. Okay, so sometimes it's helpful. I'd say it's helpful 80% of the time. So distance equals rate times time. So we have rescue boat, and lifeboat. Okay, and we know the rescue boat's rate. What's rescue boat's rate? Wait, look at it again. It's rate. Well, no, totally. But what's the number in the front? Yeah, so 29. And if you want to make life easier, as long as this isn't a mean problem, but watch out for mean problems, is all right. I got kilometers and I got kilometers per hour, and everything's in terms of hours and it's all the same, right? They're not being mean, and they're like, um, it's like having you switch it to meters. And yeah, having you switch it to second, right? Because if that's the case, you're going to want to write units in here. But because it's all the same, and you might be experiencing this from physics, you can leave it out and it'll make things easier. But always be aware of the mean problems. Okay. Okay, what's the lifeboat's rate? Okay. And I don't know the distance traveled. Do you know the distance traveled by the rescue boat? No, we don't know that. Do you know distance traveled by the lifeboat? No. But um, we do know we know the distance between them. I mean, we know like one we know this distance, right? Yeah, we know this entire distance right here. Yes. Wait, let me look at a better picture. Here. The distance between them is 71. We're stopping the stopwatch when they're 71 apart. That means that this little guy right here can walk on water. He goes over here now. Yeah, it's like the guy with the stopwatch goes and then gets a measuring tape and says, "All right, guys, let's see. How far are you guys? Oh, you guys are 71. Cool." Okay, so let me go down here. So if I draw a number line, kind of a number line, and if I have this distance, I'll say it's 60. Definitely not to scale. Um, I'm just making it up. So 60, and it has nothing to do with making it up in this problem. You don't have to make up. I just want to conceptually explain something to you. Um, and I'll say that. So yeah. So from here, like this part right here, this red part is 60, and this little piece right here, remaining, is no 11. 11. Hey, what's 60 plus 11? Okay. Now, and let's say this is. So we know together it's 71. Now let's say that we don't know that this number here is 60. So I'm going to go ahead and erase it. And it's right. But so I'm going to call it x. So we do know that x plus 11 equals 71, right? So then we can go like this, and we could say that x is equal to 71 minus 11. So x is equal to the total between them minus the other one, right? So x is the total distance between them minus the other one. And that's how you can get your 60. So I don't know like how much the rescue boat went or how far the rescue boat, how far the lifeboat is, but I do know which one traveled more distance because it's moving faster, right? All right, so I'm gonna make that like my x. Okay, so I'm gonna call that x equals rescue boat distance. Rescue boat distance traveled. Um, yeah, I still think it works the other way as well. But it's if you always know which one's going faster, make that your bigger one. Make that your x. Uh-huh. So I know that this is yeah, so that's x. And then this one over here is what would the lifeboat be? And honestly, it doesn't really matter. I could have made the lifeboat X. It will work out the same way. See, like over here, I could have been like, oh, I want to figure out what W is, right? And uh, yeah, so it would just be, if I had done it the other way around, and I had gone like this, and I called this W, and I called this 60, and the whole thing is 71. I know that W plus 60 equals 71. See, it'll work either way. Yeah, but I don't know, that's something I do, but I actually think it's the same either way. The biggest possible minus whatever the rescue boat did. So, yes, do you understand that? So it's like the longest possible minus what the other one did equals, you know, what the lifeboat does. Okay. Okay, so it's going to be 71 minus x. And and then the cool thing about this problem is that this is actually the same as this. Because do you get that? Because that's this guy's time. It's the same. They traveled the same amount of time. One is going faster than the other, but they're traveling the same amount of time. Do you get that? Okay. Okay. And then all you need is two equations, and we got them. Sometimes like you'll see some where you have to like add these two things up down below and get like a 2t or something. Not if you could ever fill up these squares like this, then you're set. Like these, if you could fill up all of these, you're good to go. Because now you got your equals right here, and your equals right here, and you do a system of equations, and you get your x and your t, and you're done. So you go x equals 29t, and you have your 71 minus x equals 4t. And you don't have to do a system, actually. Huh? Oh yeah. um, in this case, substitution is probably easier. So you could just go like, I'm going to drop that 29t. I'll just replace x equals 29t, so I'll replace this x with that 29t. Yeah. So 71 minus 29t equals 4t, and plus 29t plus 29t. 71 equals 33t. Really? So that's gone. So you got, all right, so you have 71, so t is equal to 71 over 33. But if you do that and you're not going to exactly get your minutes, so then you got to deal with the minutes because they made this problem a little more difficult. So wait, oh, I punched it wrong. 71 over 33. Okay, cool. So 2.1515. All right, so 2.151515. All right, so then it's 2 hours and 0.15151515 of an hour. Well, if you could do it like this, like chemistry style. I think if you watch your units and you go 151515, that's 0.151515 hours over 1 times. So you're right. So 1 hour is 60 minutes. like that. And then if you do it like that, you know you did it right. And you multiply. So 0.151515 times 60, 9.0909. Yeah, exactly. 2 hours and 9 minutes. Or 2.151515 hours. Yeah, exactly. You'd be the second one. This one, right?